so let me I'll go over to the document camera. We'll do some hints and we'll see what's going on here. Okay. So I think Paul had a very good idea of how to approach this, and his group, of course. I think that's definitely in the right direction. And there are multiple ways to prove this, which is why it's kind of a fun problem. Also, it's pretty foundational. Let's look at some of our tools as we think about it. So, and how we would do this. So let me ask you a question. So Paul, in your proof, did you end up using axiom 3 from the axioms of probability?
So no, we started with the expression that we wanted and then used Bayes' second theorem to reduce it down to the thing I told you.
Oh, I see.
Then,
okay.
So we hadn't gotten to there yet. Like
Yeah.
independently, I could show that using like kind of axiom 2 and axiom 3, that the sum of the probability of F1 equals 1, but we couldn't. I needed that jump from probability of F1 to probability of F1 given A.
Right. No, that makes sense. So you're using axioms. Well, let me do a few hints here. I don't think I'll do the entire proof for you because I think it's good to leave some things, leave some history for you all to think about. But let's kind of put this in context a little bit. So again, the first hint. I mean, if I was being elliptical and Socratic on Piazza, I might just say use axiom 3. But you already did use axiom 3. So that's a hint to people who are stuck. So again, let's look at axiom 3 again. We have the notion of sequence of pairwise disjoint events, infinite sequence, A1, A2. Then the probability of the infinite union is equal to the infinite sum of the probabilities. And of course, I want to remind you that this thing here is a countable union. And this thing here, of course, is an infinite sequence, which should make you think immediately of streams. And of course, we're adding here, so this is accumulate. And without axiom 3, you don't have probability, right? And countable unions are definitely mysterious things, but the reason I showed them to you is so that you could understand how probability works, and then you're poised to do AI, ML, statistical inference, data analysis. Without that, you're not prepared. But now that we know that, we can just use it. So basically, the top hint is to somehow use axiom 3 in some sense. I'm going to see what I can do here. So let me give you some hints, kind of sketch out kind of how I would think about this. So I'll sort of write some hints over here to how I might do the proof. So I'll write some steps, and maybe I'll ask you to shout out what the reasons for these sets are. So the first thing I'm going to do here is I'm just going to take this sum, and I'm just going to rewrite the sum like this. So why could I do this? Why is that a correct step?
It's just replacing the rule you put at the first line into the formula.
Right. It's exactly. It's the definition of conditional probability. I'd write that my reason out like this. And by first line, you meant this, right?
Yeah.
Yep, good. So good. So let's expand that. Again, this is a proof sketch. We can go into detail about everything, but that then is equal to the following thing. We can write that as the probability of A intersect F1 union all the way up to union A intersect Fn. So why can I do this? Right. So this is kind of the key step here. So this is a little less obvious. Does anyone see why this is true? There's sort of two reasons that nestle together to do that step.
If all the FIs are pairwise disjoint, then A intersect FIs, all those must also be pairwise disjoint.
Yeah, that's exactly right. So let's write that down because that's the first key observation. So FIs are PD, pairwise disjoint. This implies the A intersect FI are pairwise disjoint. And then there's a second thing we're doing here. Like, how can we break it up as the union? What rule are we using there, right? Can you see the second thing that we did?
Is that different from using the axiom number 3 that we're talking about?
Yeah, we used axiom 3. I'll just say apply. So this is a pretty standard paradigm in trying to use, tools that, theorems you've just been shown is that we'd like to somehow use axiom 3, but remember, proofs are programs and programs are proofs. And just same way that programs have types and preconditions that have to be satisfied where you can call them without something bad happening, the prerequisite or the input or the type for axiom 3 is I need a sequence of pairwise disjoint events. So I have to use the reasoning here in step 1, as was just pointed out, that these are pairwise disjoint events. And then I can just basically go from sum to unions. So basically I just went from sum to unions using axiom 3. That's sort of the key step. The rest is manipulations in set theory, including the step that Paul already talked about. I'll just sort of sketch them and you have to prove these, but basically that can be simplified to the probability of A intersect F1 union all the way up to Fn, right? Just by set theoretic manipulations. And then that thing is going to be equal to, and again, let's credit Paul for this and his group for the observations. This thing here, of course, and this is what we were just talking about before I asked you all, this of course is equal to omega because they make your entire outgrowth space. This is just equal to the probability of A intersect omega, but that's everything, that's just the probability of A. So this is a sketch of a proof. You could do 2 or 3 lines justifying each step. I mean, the first one you don't need to justify, but this requires a little bit of justification. But that's the bones of how one might go about proving it. There are a couple of other ways too. But with that in hand, once you work out the details, we have a proof of the law of total probability that derives directly from set theory because we have to be able to simplify what sets are and do some reasoning like this, that if all the FIs are pairwise disjoint, when you make them even smaller by intersecting them with A, those guys, the intersections are pairwise disjoint as well, as was eloquently stated earlier. Then we apply axiom 3. Remember, this is a way of going back and forth between unions and sums. Now, don't be afraid that actually the way it's phrased is very general. It's going between countable unions and infinite sums because you always truncate the sums by having things that we don't care about in there. So we have a sum here. We want to go to a union, manipulate the union with set theory. We're basically running the equation backwards in some sense by satisfying it. So that's the intuition I would give for one way to prove it. I think there are other ways as well. There's also proof of this in the lecture notes that is similar to this, but I think this is a little bit simpler. What do you think? Do you think you believe this proof? Do you buy it? And do you think that if there's some details you could fill them in? Do you have any questions about this? Yeah, so it depends on the level of proof that you'd want to do. Oh, it seems done to you? You wouldn't do anything? Well, I guess that's a really good question. So Tommy asked, what other level things would you do? So I basically think that your colleague articulated this argument very well. But we've already been through why these are pairwise disjoint. I think that the main detail, what does it mean to apply axiom 3? So I'll just do it for you. I might, in this step here, when we actually applied axiom 3, I might have said, so you have to actually have a sequence. I have to say what the sequence is. So I'd say let the sequence be A intersect F1, A intersect F2, all the way up to A intersect Fn. And then after you're done with the finite stuff, you have to have null sets all the way out to infinity. Sometimes I have to actually give a sequence. This sequence then has the correct type to go into the theorem. So it's sort of obvious, I think, to a mathematician, if you say it this way, it's going to all work out. But basically, you want to make sure you're satisfying the type of the theorem. And I think that in a proof, we'd like to see, hey, that's how I would do the sequence, how I construct the sequence so I can invoke the theorem. Otherwise, it's a little bit mysterious. Invoke axiom 3. Well, what are you applying it to? We have to apply it to a sequence of pairwise disjoint events. Here they are. Let's actually just line them up and say what those events are. So that's what I'd say would be an additional detail in red that would make this a pretty rock solid proof, in my opinion. Does that make sense to you? Great. Any other questions about this?
How do you know that the last step is true? Is that because it's P of A?
This step here?
Yeah.
This step here? From here to here?
Mm-hmm.
It's a great question. Well, so let's think. So always good to think about this. Well, so this isn't a proof by picture, but I will nevertheless draw one. So omega is your entire universe, and any event A is a subset of that. So you always have the situation for any event that A is a subset of omega, right?
Okay, yeah.
And so because A is a subset of omega, we have that A intersect omega is equal to A. So that's my reasoning for that.
Thank you.
But yeah, always good to ask these questions because want to make sure you're convinced. Any other questions? Well, we're pretty much at the end. That's basically what I wanted to cover. Let me remind you that Alex and Abe will be giving the class on Wednesday. I'll be sitting in the back, so to speak. It should be exciting. And we're done for the day. What's next in the class is we'll have essentially problem session, a discussion of the material that would help with PS6, namely hidden Markov model, Viterbi algorithm, some more conditional probability, and some exercises that should be, I think, pretty useful to you. And then next Monday, I believe we have 3 more lectures, more or less. I'm going to take what we learned and help you apply a little bit to algorithm design. Of course, you've been designing algorithms all along, but I'd like to explore with you, given our newfound understanding of mathematics, set theory, and functions, how we could develop some algorithms for hopefully interesting problems, including some coding interviews, some robotics, some other kinds of problems, and see if we can use mathematics a little bit to develop algorithms that are both better and those that we can have a more sophisticated understanding of in 3 more lectures. Reminder, problem set 6 is out, due in 2 weeks. And with that, I'm going to pause the recording. I'll thank you for listening, and I'm happy to I'll stick around for office hours, and I'll happy to discuss with you anything about probability, this lecture or the class. Okay, well, great to see you all, and I look forward to seeing you on Wednesday.